I was quite enjoying that music. Happy Monday. How's everybody doing today? I hope exam week went well for everybody. So let me know if there are any questions or anything. I received a few questions, but otherwise, seemed like everything is going well. So now let's continue with chapter 13 today. So we're doing alkenes and alkynes. I apologize, my allergies are out of control today. So we have alkenes. So an alkene is a double bond. So the simplest one is going to be ethene here. We have our double bond. And so this is where your models might come in handy. So what's the geometry? That's what we want to know here for ethene. And this is really important. And you could follow the rules too that we've kind of been learning. So you'll see this pattern. We'll go over the hybridization. But I just want to emphasize that this structure is planar. Let's switch over. My cat is bombing. So here's ethene. Notice, right, we have a representation of our double bonds. And so this gives us a planar structure. Just place it there for a second. So this means, right, that this is all planar and that this angle is going to be about 120 degrees. And we can say that these carbons are sp2 hybridized. So just a recap, sp3, that gives us that tetrahedral carbon with 4 distinct atoms attached to it. Now we have only 1, 2, 3 things on it. And so this means we have 3 orbitals coming together to give us this sp2 hybridized orbital. And then if we compare that to an alkyne, and so again, carbon has to make 4 bonds. So now an alkyne has a triple bond. And so this geometry, I apologize. So this geometry now would be linear. Of course, 180 degrees there. So now let's look up naming again. Sorry, let me move my cat. So for naming, it's all the similar rules as before. We just want to give priority to our double or triple bond. And so let's look at this compound here. Draw this out. Okay, my cat's being really obnoxious. Oh no! Okay, technical difficulties. Sorry. Now my cat hit my headphone. All right, so here is our compound we're looking at. And so once again, we have to identify the longest chain, but except our longest chain needs to contain this double bond. So we're not going to do 1, 2, 3, 4, 5, 6, 7 or anything like that. I think I have too many carbons because I didn't want to draw this. Sorry, let me take off one of these carbons. So this gives us, it would not be 1, 2, 3, 4, 5 or 6 here. 1, 2, 3, 4. Oh, I put too many carbons. I apologize. I was looking at my example. There we go. So this is our chain. And so instead we want to identify the longest with the alkene. And so we could go the other way too, right? 1, 2, 3, 4, or 1, 2, 3, 4. So either way, it's 4 carbons, so it doesn't matter. And so this gives us something of butene. So then what would the name be? So we want to assign priority to our alkene here. So this is carbon 1, 2, 3, 4. And then now we have our ethyl group. So 2-ethyl butene. So let's look at another example. Let me draw out another example. So the other thing that you want to get good at doing, so you kind of have this abbreviated structure and you want to be able to translate kind of this abbreviated structure into more of its 3D geometry. And so you could just redraw this out. So you can clearly tell which carbons are bonded to who. And of course, everyone should have 4 bonds. So write that CH, that's bonded to a methyl. Carbon, double bond, hydrogen there. And make sure write 1, 2, 3, 4. That all looks good. I'm drawing this a little funny. So there's our structure drawn out. So let's identify our longest chain again. So I'm trying to see what contains my alkene. So I could do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So either way, that won't change anything. And then let's see, I could go, I probably want to assign it going 1 here since I have this methyl group that I'm looking at. And then I also want to try to give the highest priority to my double bond. So this looks like 1, 2, 3. That's, yeah, and that'll give us right 1, 2, 3. And that gives a higher priority to this methyl group. So now we've counted our carbons. So let's name this. So we have a methyl group. It's on the 2 position. So that's going to be 2-methyl. And then we're going to put 3 to indicate where our double bond is. So 3-hexene. You might also see it or 2-methyl hex 3-ene. So I think this is an older naming convention, but this is still used a lot. But you might also see it like this. On an exam, I would want to accept both. And so if the test doesn't take it, or I'm not too picky with these little dashes and everything. Yes, I want you to practice them, but you know, I understand entering it on a computer. Sometimes they can grade it really harshly, so just let me know if there are any grading errors. I'm happy to correct. So ironically, I'm allergic to cats, by the way. So my allergies are crazy. Let's do another practice. So give me a second to draw this out again. All right. So now we have 2 double bonds in this structure. So we could go 1, 2, 3, 4, 5, 6, but that gives the lowest priority to our double bonds, and we want this to be highest priority. So what do we go? 1, 2, 3, 4, 5, 6. So that's the better way to do it. So that means we get 1 and 3 for the start of our double bonds. So now let's label it. So we have 5-methyl here. And then there might be, again, several different ways you might see this. So we want to write 1, 3. And now it's going to be hexa. And then to indicate how many double bonds, it's going to be diene for 2. So if you had multiple ones, right, you could do triene, tetraene, etc. Or if we're going with maybe the newer convention. So it would be 5-methyl hexa 1,3-diene. So either one of those is perfectly acceptable. So let's look at the cyclic ones now. So let's try one. So what would this one be? So we can assign our priorities again. So we have to decide, are we going to go 1, 2, 3, 4, 5, 6? Well, then that gives us low priority to this double bond. So instead, we want to go 1, 2, 3, 4, 5, 6. And so now this is going to be 1,5-dimethyl. So we have 2 methyl groups. And then cyclo. So we have 6. So cyclohexene. So let's see about when we have 2 of them. How would you name that? So what would this one be? Take a minute or so. So now we got to label it again. So assign your carbons. So 1, 2, 3, 4, 5, 6. So our double bonds start at 1 and 3. So this is going to be 1, 3. Cyclohexadiene. Or that cyclohexadiene. 1,3-diene. So I'm looking at other examples that might come up. Okay, let's try this fun one. Then we'll look at cis versus trans isomers. See if I can draw this. Oops. See if I drew that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I believe. So let's label our priorities. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a ring. So 1 cyclodecene, and then 4 ine for our alkyne. So the other thing that will come up is cis versus trans isomers. And so let's kind of see why this matters. So now I'm going to make 2-butene. So what would this look like? 2-butene. This is where your molecule kits come in handy. So I encourage you to hopefully try to make your molecule. So let's look at it together. So here's one version of 2-butene. So we have 1, 2, 3, 4. Start for 2 there for a double bond. And so notice the 2 methyl groups are on the same side. And so we could draw this. So this would be the cis isomer. And this is often, like if you have, we'll look at them in a second, but like natural fats, for example, if they are unsaturated, usually they form this cis. And so what other way could we do it? What if I swap the position of the hydrogen and the methyl? So now I get something that looks more like this. So it has a little more zigzag in it. So this would be the trans isomer. So now they're on opposite sides. And they're not interchangeable by rotations. Remember, we can't just rotate that double bond. So they're just 2 distinct isomers. So now let's see how that plays a role in different fats. So this first one that we're looking at, so this is stearic acid. So this is what's called a saturated fat. And so it's saturated, right, because all the carbons have hydrogens on them. And so this stearic acid fat so this is found in animal fats and vegetable fats. Also found in shea butter, so that's going to be like the vegan source of this type of fat. And so the other important thing about stearic acid is it's going to have a high boiling point. And so let me look it up for reference. So it's let's look at the melting point actually. So its boiling point is also pretty high. So all these are related, so we'll go into them. So its melting point is 69.3 degrees Celsius. So this means it's going to be a solid at room temperature. And so why this matters too. So there's a couple of things that we want to look at. So first of all, if we recall back to our lab, our saponification lab, right, we said we needed this carboxylic acid group, and that's what was undergoing that saponification. And so that's one relevant point. So that's how we turn, right, our fats into our solid soap there. But then we want to understand, well, why is this melting point so high relatively speaking? And that's because of this saturation. So notice it goes up and down, right, in the zigzag pattern. But you could stack another one kind of on top like that. So you can see how they can stack. And so that means that they have a lot of surface area, so they have strong intermolecular forces between them. And let's compare this to oleic acid. So this oleic acid is found, I believe this is olive oil. So let me look up the boiling point. And remember, this is primarily olive oil. So olive oil is about 70% of this. But its melting point, so we can compare, is now 13 to 14 degrees Celsius. So what accounts for that huge difference as we go from saturated, so now this would be called unsaturated, since it has a double bond. So in this case, this oleic acid has one double bond. And so this double bond, we mentioned that this is going to be in the cis conformation. So you could tell it's on the same side like that. Let me go back. So now that it's kinked like this on the same side, giving us a cis here. So now we can't stack as readily, right? So if we were to take another oleic acid here And then now, kind of try to stack it or something. And it's going to be a little off now. And simply because they can't stack as well. So now you have that disruption, right, between compared to this one where it's all saturated. So now it's got a little kink. And so now they can't stack as nicely. And so now that disrupts those intermolecular forces. So the other thing is they have pretty similar intermolecular forces. So this is mainly going to be van der Waals. We have some hydrogen bonding here. But for the most part, they're mainly nonpolar. And so we're just kind of comparing how well can they stack. And so this little kink means that this disrupts our intermolecular forces. And so that greatly lowers its melting point. And then if we compare it to linoleic acid, sorry, lost my cursor. And its melting point is -5 degrees Celsius. So this is another plant derived. So it's linseed or flaxseed oil. But now what we care about is that it has 2 double bonds. And so now this disrupts that nice zigzag pattern even further. And so that's why it has an even lower melting point. And, you know, roughly this is why, and I don't want to go too much into diet since there's all sorts of science out there, and honestly, the fat thing gets a little controversial. But kind of the general rule is that you want a fat or an oil that's going to be a liquid at room temperature. If you have something that's a liquid, right, you know that it's not saturated, and that's supposed to be better so it doesn't solidify in your arteries. And actually, I'm not going to go in order of your book. No, this is lycopene, by the way. Lycopene. Well, let's revisit lycopene. But while we're looking at these fats, I want to get back to trans fat. Because we'd been looking at these isomers, cis versus trans. And so what does that mean when you have trans fats? So what's pretty interesting about these trans fats is they're, for the most part, synthetic. So I think there is a small amount of naturally occurring trans fats, about maybe 5% of animal products, so that's going to be naturally occurring. But if we're talking about, let's just say our good old Crisco here. So Crisco is made from taking a saturated fat, and then they do unsaturation to add this double bond. The problem is when you do this synthetically, this gives you a trans double bond. So remember we had said that naturally, usually we get this cis, as in our oleic acid, right, from our olive oil. And so this is why people are particularly concerned with trans fats, and some people believe trans fats, are the worst of the worst. And so if you're comparing, let's say a trans Crisco versus just like animal fat that's natural and, naturally saturated, people would argue that the animal fat is actually healthier because of this trans double bond here. And so there's, again, our stearic acid for comparison. So it's going to be a solid compared to our Crisco there. So there's a lot of naturally occurring substances that are alkene based. So again, this is lycopene, and this is what gives tomatoes its kind of red color. So lycopene mainly absorbs all other colors. So it would absorb blue, green primarily, but not red, and hence why lycopene is red. And y'all remember that, right? The color wheel. Let's talk about it real quick. It should be a recap, but so how colors work. Oh, my cat is being really obnoxious. Wow. I don't know why I'm struggling to find us a decent color wheel. And so how colors work is you basically see every color that's not absorbed. So in this case, if we're looking at lycopene, which is a red substance, this means that if it's red, it's going to absorb everything else, right? So light is all the colors. So that's also important to know. So light is all the colors. So it's coming in, and then this lycopene can absorb everything on this side. So a lot of the blues, the greens, purples. And then what's left is what we see. So since it doesn't absorb a lot of the red, that's what is reflected back at our eye and what we see. And so there's lots of other substances. So your book also mentioned estrogen. So you have many of these are used for hormones. So let me know if you want to go over any of those. Welcome in the chat. Let me know if you have any chemistry questions. So let's start going over some of these reactions. I think we'll get through these addition reactions of alkenes today. So let's start with hydrogenation. So hydrogenation is when we have a double bond here. And then in the presence of H2 and a catalyst, so this catalyst is typically going to be either palladium or platinum. And usually they just kind of sell it as this little ready to go hydrogenation catalyst, really convenient. And so now we just add hydrogen to both carbons. So relatively simple there. So we break our double bond. And then so halogenation, this most readily occurs with either bromine or chlorine. And we'll probably do this in lab when we get to it. And so not this week is functional groups. But after that, we'll do some tests for alkenes. And one of those tests is to add bromine to it. So bromine is this really dark red liquid. It's kind of a fuming, angry liquid. But if you add it to something and it disappears, that indicates the presence of a double bond. So let's look at this. Let's look at this halogenation. So we have our compound here, propene, and then we're adding chlorine across these two double bonds. But what we actually want to do, so let's take a look at the mechanism because we want to understand how we get our products. So let's take a look at the mechanism. So now this is we're adding it to butene. And sometimes you see this E or Z. So E means same side. Or sorry, E means opposite. Z would be cis, same side. So we have our trans isomer here. And this is where your molecule kits come into handy. So we're looking at it, right? We're looking at it like this. This one's going back, this one's going in front. So let's draw this. Let's draw this over here. And so the first step is it forms this, it's called this brominium intermediate, and it's actually positively charged. So you have your bromine here, or chlorine. And so this double bond, these electrons are going to go to bromine. So now the bromines break apart. And then this one attaches back. So we form this carbocation intermediate. And so the thing is, this is below, right? So we have our bromine kind of down there, intermediate. Well, now our bromine has to attack from the other side. So this is our intermediate. We're kind of looking at it 3D. So this is on bottom. And if this is on bottom, this means that now this other bromine is going to finish the reaction and attacks from the direction that is anti. So it's going to come in from the top, right? And then it could either attack here. That's going to, of course, break this bond and give us this product. or give us this product. Now, in this case, they're identical by rotation. But this may not always be the case. So you might have something in a ring where the stereochemistry does matter. So now if we look at this one, so this is Z-butene. So now they're on the same side. Same side. So now once again, that bromine is either going to go in from the bottom or the top. And then examining, so we're here, this is our intermediate. Now our bromine can either go here or here. So it would go here and leave that anti. So you would get something like this. And so this one looks like stereochemistry does matter. And so you might have to rotate it to convince yourself. So if you were to flip this and rotate it up, right, that bromine would be up. But now this carbon would be back here instead of the hydrogen. So they have a little bit different chirality. And this is a little advanced, but it's really important that we look at it now. And so just do that. Just practice drawing both the products. Are they the same? Are they different? That's what you have to determine. Now, another scenario that I didn't see in your book, but I wanted to go over. So these were all done in the presence of an organic solvent. So if you notice, it tells you what solvent they're in. So this one uses, this is DCM, dichloromethane. So usually this reaction takes place in some sort of halogenated solvent. I think chloroform would also be appropriate, but usually DCM is really popular. But what happens if you did this halogenation reaction in the presence of water? So this is halogenation in water. So that gives us a different product. So let's understand this. So we have our cyclohexene. So plus bromine. So now it can do similar sort of mechanism, right? Forming our intermediate here. Right, so a carbocation intermediate. So this is, let's just say this is down below. So now we have water. So water can autoionize, and so we can have our hydroxide then attack. And again, it's going to go anti. So if it attacks here, that's going to kick that bromine off. And so now they're opposite sides. So that's why this is up and this one is down. Or it could attack from the other side, giving us this other combination. And so now we get half halogenated, half OH. So now looking at this one, which one is going to be So we have a couple of things that we want to look at. So why is the chlorine on this carbon and not this carbon? So let's look at that. So again, right, this can form our carbocation intermediate. So this attacks chlorine. These go back. Chlorine makes a bond here. So now this is our intermediate. And so when our hydroxide attacks, it's going to pick the one that's more stable as a carbocation. And so let's break that down. So now we're going to say attacks. And this will come up again. So more stable. And well, what does this mean? What's a carbocation? So this is just a positively charged carbon, but we want to attack kind of the one that's more stable. And well, what makes something more stable? So a tertiary carbon is the most stable. Then it goes down. And so this tertiary one, since it's attached to 1, 2, 3 carbons, that makes it favorable. So it's more stable, so it can balance out that positive charge, as opposed to attacking this one, where this is only connected to 1, 2. So that'd be a secondary carbon. And I don't want to say that it can never happen, but, you know, in this case, this one is going to be the favorable product. So this OH will attack this carbocation. And then, of course, we get that opposite stereochemistry since this OH is coming from, in this case, the top, if we're looking at this from the bottom there. So then you should have opposite stereochemistry and get both of these results. So depending on whether you go from the top or the bottom, since both, again, are possible. So does that make sense? You really have to think about these structures in 3D, but that's why I highly recommend a molecule kit. You can always talk to me about which one you like. Again, it's mainly personal preference. I like this one. If you're moving on to OChem, this one is really helpful for more complex structures. But this other kit is really nice for our Vesper geometries and making our Lewis dot structures. So now we're looking at hydration. So hydration, once again, follows with a similar pattern here. So let's look. Now let's look at the mechanism. So hydration, we're just going to add this water across. We could also add, methanol or ethanol, something else like that. And so let's check out the mechanism. Let me get rid of this. And I can't emphasize this enough. I don't think I've said it enough, actually. So our action always starts at the electron. And so this is this little cat H3O+. This means that it's acid catalyzed. And so again, water can't undergo autoionization with itself. And this is the nice thing about water in organic chemistry, right? And water can act as an acid or a base. And then if we catalyze it, that kind of helps it along. So in this case, this is acid catalyzed, some phosphoric or sulfuric acid. Welcome, welcome. Feel free to ask questions. And then, so what we see here, so we're starting with our hydronium, positively charged water here. And so now this is primed to undergo attack. So we have electrophilic attack. So these electrons want this positive hydrogen, so they're going to attack that here. And then so when we make this intermediate, again, we're going to form that more stable carbocation. So this is what dictates what happens next. So that hydrogen attaches to our kind of least stable one. So in this case, we have a tertiary versus a secondary. So our hydrogen attaches here. And then that gives us our intermediate. You always want to show your electrons. Now your electrons have formed a bond with hydrogen. That kicks these electrons back to water. So water is neutral, just hanging out. So that's what's drawn here. And let's draw our carbocation. So now this is stable, but of course, this carbocation is going to be reactive. And so in this case, water actually is going to do the action here. So water has those double bonds. And hopefully you're seeing that, right, these basics of Lewis dot structures, now they're really helping us with our OCHEM mechanisms. And so one of those lone pairs from water is going to attack this carbocation. And so that gives us this intermediate species here. So all we've done is we drew a bond. And so now we have a positive oxygen again. But then this can be readily deprotonated to give us our neutral product there. Excellent. Oh, was that all our reactions? Believe so. That was fast. Let's look at our next set. I guess we can finish the chapter today. So let's look at polymers. So polymers now, they are generally these alkene monomers that are then stitched together using polymerization reactions to react them with that double bond and then create these polymer chains. So for example, you have polyethylene. That's one of the more common ones. So polyethylene, I believe that's the one. Or is it polypropylene? Sorry, trying to remember now. So I believe polyethylene is used for plastic bags, bottles, toys, and then polypropylene is used for those masks. I hate the mask. So those masks that everyone is wearing, made out of sorry, I wanted to look it up before I told you wrong. Oh, come on. How come I can't find it? I'm pretty sure it's polypropylene. Yeah, but those masks are made out of plastic essentially, and they blow those fibers really, really thin, and that's what gets them kind of their electrostatic charges. So there's polypropylene, and then you also have polyvinyl chloride, or PVC, as you probably have heard of it. And so you probably know PVC pipes. That could also be bags, floor coverings. And then we also have polytetrafluoroethylene, so PTF, which is used in nonstick coatings, but personally, I'm not a fan. I don't think that these chemicals are quite stable to high heat, so personally, I don't buy anything with nonstick coatings. And then everything is classified by these plastic identification codes. So these plastic identification codes are supposed to help separate things into recycling. So if you have the symbol 1, for example, that's for the PET plastic, so the polyethylene based plastic. And so again, these are your soft drinks, your water bottles, and then if you recycle it, they can go into sleeping bag filling or clothing. And then high density polyethylene, so that just means that it's packed usually tighter together. And so this is going to be harder. Shopping bags are made out of this. A lot of bottles, and then they can be recycled into recycling bins and containers posts. Now PVC, so this can be tougher. And so notice too, as you go down, usually it's harder and harder to recycle. So these can still be turned into speed bumps, binders, mud flaps, all sorts of things. So low density polyethylenes, now this is going to be soft and flexible. So that's clean rack, garbage bags, so those are a lot thinner, and then they can be recycled into bin liners. Number 5 is polypropylene. And so this softens at 140 degrees Celsius. So again, notice that higher melting point. And this could be straws, kettles, lunch boxes, packaging tape, and then recycled into trays and battery cases. And then polystyrene. The polystyrene is actually kind of difficult to recycle. That's why it's down here at the bottom. So polystyrene, we have CD cases, plastic cutlery, and the foam polystyrene. So those are kind of nasty. People have tried to move away from these since they're, again, more difficult to recycle. And then 7 usually is difficult to recycle. It could be some sort of combination too, some resins. But you could also recycle these. And so what's been one of the big barriers for recycling? It's kind of been the issue. Because it used to be, even this is, of course, an ideal scenario where you separate your plastics based upon all these numbers, but then the question is, okay, well, where does it go? That's kind of been a big problem, as we used to ship a lot of our garbage and recycling overseas to like China and other Asian countries, but there's a lot of trash in the world, so they no longer want our trash. And so this has been difficult for companies to figure out what to do with this trash. I think people are looking to be innovative at home. So those of you that are students, right, you may want to look into recycling and how we can do it at home, cheaper, more efficiently, and make cool products into it. I know glass is also an issue. So I've seen some stories where we've been doing some local glass recycling in the US. But all these, I think, are great ways to innovate. And the other thing is, there's I don't know if you've ever heard of the term microplastics, but these plastics are also difficult since they just kind of get smaller and smaller and smaller and just become like little physical pieces as opposed to fully breaking down and degrading, since these bonds are very strong. So this polymerization process makes these bonds very strong. So now it takes a while to break down since you have to break apart these bonds. Lots of challenges. All right. Let's look at our last set of reactions. And so now we're looking at benzene and its kind of derivatives. So benzene is really important. I think we've brought it up a few times. So this is benzene. It's an aromatic solvent. It's also carcinogenic. It's a very good solvent though. So back in the day, organic chemists used to clean their hands at the end of the day with benzene. It's called the benzene dip. They just give their hands a nice old rinse in benzene to get them clean. Don't want to do that. Benzene's carcinogenic. So, I think they realize that. And so benzene can have different derivatives. So let's look at, if you stick a methyl group on it, now we have toluene. But then you can have other substituents. So now if you have a ring, and let's say we wanted to do chlorotoluene, so we could have what's called ortho position. So the ortho position is just 1 over from our first substituent. So this is ortho. You could also draw it on the other side. So both of these are the ortho positions, here and here. Ortho, ortho. Now the meta is now the second position. So this would be meta. Could draw it again on the opposite side. Still meta. So the same by rotation, but I just want to make it really clear. And then our last type is para. So para is just directly across. So this would be parachlorotoluene. And so you could refer to this as orthometa or para. So the other interesting thing is that these aromatic compounds do not want to break their double bond. So if you can't hydrogenate them like you would just a regular alkene, since now this is an aromatic system. So instead, if you try to do a halogenation reaction with benzene, what you would get is you get this substituted here. So we had benzene plus bromine and iron tribromide. That would give us this product here. We could also do the same with nitric acid. So undergo nitration reaction in the presence of sulfuric acid. And so that gives us NO2 here added. Or we could do the same and do a sulfonation and add sulfate here. All right, I think that covers it for this chapter. So Wednesday we can do some review problems together, go over any questions you have. And so let me know if anything seems difficult, or if you have questions from the section, and we'll go over them on Wednesday. So I'll hang around on stream in case there are questions. Just email me if you want to set up office hours. I do have some meetings today, but I'll still be available. Again, just email me so we can set a time. So thank y'all and have a great rest of your day.